Hi guys, in this video we are going to be talking about probability. So we are going to be looking at what probability is and how to determine basic probability. So let's go ahead and start with the definition. So probability is the portion of specific outcomes and to all of the possible outcomes. So like when we talk about flipping a coin and I say what's the probability that the coin is going to land on heads, we always say that there's a 1 out of 2 chance or 1/2 chance or a 50% chance because a coin has one head out of 2 options, which would be a head or a tail, so there's a 50% chance. And probability is all based on fairness, so this is assuming that you have a fair coin. The same thing like with a dice. If I wanted to know what was the probability of rolling the number 6 on a dice, well, there's one number 6 on a dice out of 6 different numbers, so there's a 1 out of 6 or 1/6 chance that I would roll the number 6 when I rolled a dice. So we look at the probability of the definition, or the formula I guess you would say. The probability of an event A happening is the number of outcomes classified as A and over the total number of possible outcomes. Again, so thinking about that rolling a dice, and I could do, but my probability doesn't have to be like a specific number. I could say what's the probability of rolling an even number on a dice? Well, there are 3 even numbers on the dice, 2, 4, and 6, so that would be 3 out of 6, which would reduce down to 1/2. So there's a 50% chance that when I roll a dice, it will roll an even number. Okay, so let's do an example from a deck of cards. And I know a lot of people maybe don't know all the cards that are in a deck of cards, so I do have a picture that's going to come up here in just a second, but we're going to find the probability of drawing a jack from a deck of cards. So we want the number of jacks in the deck divided by the total number of cards in the deck. And notice that over here in our formula here, we've got P, so that just stands for probability, and then in parentheses we're doing a very shortened version of what we're asking for, in this case jack. We're not specifying a suit for our jack, so all we just care about is that it is a jack. Alright, so here is a deck of cards kind of drawn out for you. Notice that we have 4 different suits. We have the hearts, the diamonds, the clubs, and the spades, and each suit has an ace and then the numbers 2 through 10, and then they have a jack, a queen, and a king. There are 13 cards in every suit, so there are 13 spades, there are 13 clubs, there are 13 diamonds, there are 13 hearts. So in total there are 52 cards in a deck of cards. And then we're wanting specifically jacks. That's these guys right here. And if you count, we have 4 jacks. So the probability of pulling a jack from a deck of cards would be 4 out of 52. We always want to take our fractions and reduce them as much as possible. So we're going to reduce this by 4. 4 divides into 4. 4 divides into 52. And we get 1 out of 13. So there's a 1 out of 13 chance that we would pull a jack from a deck of cards. We can write this as the fraction 1 over 13, or we can actually do it as a decimal. So we can say that this is 0.08. And then we can also write this as a percent by multiplying that decimal by 100%, which would be 8%. So there's an 8% chance that we would pull a jack from a deck of cards. And that's actually the same percentage no matter what card I choose. So I could do the same problem and ask you what the probability of pulling a 5 out of a deck of cards. It's still going to be 8% because there are 4 cards that are the number 5. So we have the 5 of hearts, the 5 of diamonds, the 5 of clubs, and the 5 of spades. So that's 4 out of 52. So that actually doesn't change the probability based on what card it is. Now, if I go more specific and I say what's the probability of pulling a ace of spades, well, now there's only 1 card that is the ace of spades, so it would be 1 out of 52. If you have any questions about how to do the probability with a deck of cards, let me know. I found this picture of a deck of cards online, so you can just Google that and do an image search if you're unsure of what cards are in a deck of cards. So a random sampling. So this requires that each individual in the population has an equal chance of being selected. And you kind of think, well, duh, that makes complete sense. But simple random is obtained by just using a random sampling. Now, the reason I want to talk about this is because when a long time ago when we used to do drafts, we had this thing where we would do all of the birth dates were in a big bucket, and then somebody would put their arm in the bucket and pull out a birthday. But the problem is that when they did the birthdays, they started with the January and wrote them on a piece of paper all the way through December. Well, as you can see from that very first picture, that bucket is very, very full. And when you look at the people who were drafted in that 1940 draft, the vast majority of the people had birthdays after September, because those were the ones that were the closest to the top. So that would not be considered a random sampling, because there's a much higher chance that you would be chosen if your birthday was after September than if your birthday was before September. So in the Vietnam draft, they did it a little different. You can see that the jar is much emptier. What they actually did was they had 2 buckets, and one bucket had the months. So they had 12 balls or something in that one where they would pull out a month. So, and then the second one had the days, so 1 through 31, and they would pull out a day, and that particular day of the month would be the people who were born on that day would be drafted for the Vietnam draft. So they did a little different there. They learned from their mistakes. The second draft was much more random, because you had an equal chance of being selected no matter when your birthday was within the year. Okay. So independent random sampling requires that each individual has an equal chance of being selected, and the probability of selection stays constant from one selection to the next. So what that means is that whenever you, like if they did the draft when they pulled out January 2nd, they would put both January and the 2nd back into the mix, and that could have an equal chance of being selected again. Okay, so that's when we talk about independent random sampling, because what happens is if I don't replace the values back into whatever I'm looking at, my total number of outcomes now changes. So think about that deck of cards again, and I say, well, what's the chances of pulling 2 hearts? Well, when I pull the first heart, there is a 13 out of 52, because there are 13 cards out of 52, 13 hearts out of 52 total cards. But when I pull the second heart, if I don't put the one I already drew back, my probability now changes, because 1, I might not have 13 hearts in the deck anymore. Number 2 is I don't have 52 cards because I didn't put that one back. And that messes up our independent random sampling. So random sampling just says that everybody has to have an equal chance. But when we add the word independent, we now say that every single time we pull something, it has to have the same probability of being selected every single time. So that's what we call replacement. So sampling with replacement, and meaning putting that person back into the population and then pulling a new person out to make the next selection. If you have any questions on how to calculate any probabilities, just make sure to email me.